Welcome to a lesson on the curl of a vector field. The goals are to define a curl of a vector field and then also to determine the curl of a vector field and interpret their results. The curl of the vector field f is equal to the cross product of the differential operator, which you can think of as a partial derivative operator, and the vector field f. And we can determine this cross product by evaluating the 3x3 determinant, where the first row would be ijk. The second row would be from this differential operator, where we have the partial derivatives with respect to x, y, and z. And then the third row would be from the components of the vector field f. And if we evaluate this 3x3 determinant, we end up with a vector field with x, y, and z components, as we see here. And in our example, we'll take a look at how evaluating this determinant gives us this vector field. But let's first talk about what the curl of a vector field means. The curl of a vector field measures rotation or spinning effect of a vector field. If you were in a windstorm, the curl would measure the tendency of something to rotate in the windstorm given by a vector field. And the curl lines up with the axis along the axis of rotation, and the magnitude would represent the strength of the rotation or how fast it would rotate. And the direction of the rotation can be determined by using the right-hand rule, which means if you point your right thumb in the direction the curl vector is pointing, as you close your right hand, your fingers would close in the direction of the rotation. Let's go and take a look at an example. We want to determine the curl of the given vector field and then determine the curl vector at the given point. So let's go ahead and set up this 3x3 determinant to determine the curl of vector f. So the first row will be ijk. The second row will be the partial derivative operators with respects to x, with respects to y, and with respects to z. And the third row will be the components of the vector field f. So we'll have x squared z, negative 2xz, and yz. To evaluate this, we'll use the cofactor expansion method. So for this first 2x2 determinant, we eliminate row 1 and column 1. So we'll have our partial derivative operators here, and then negative 2xz and yz. Here we'll eliminate row 1, column 2. So we'll have the partial derivative operators with respects to x and with respects to z. And we'll have x squared z and yz. And for here we'll eliminate row 1 and column 3. So to determine the x component of the curl, take the partial derivative of yz with respects to y. It'll give us z minus the partial derivative of negative 2xz with respects to z. So we'll have minus negative 2x. And then for the y component, we'll have the partial derivative of yz with respects to x. That's going to be 0 minus the partial derivative of x squared z with respect to z. That would be x squared. And then for the z component, we'll have the partial derivative of negative 2xz with respects to x. It'll be negative 2z minus the partial derivative of x squared z with respects to y, and that would be 0. Let's go ahead and simplify this on the next page. So we'll have z plus 2x. This would be positive x squared. And here we'd have negative 2z. So notice the curl of vector field f is another vector field. Now we want to determine the curl at the point 6, negative 3, 1. So the x component will be z plus 2x. It's going to be 1 plus 2 times 6, that'll be 13. The y component is going to be x squared, that'll be 6 squared or 36. And the z component is negative 2 times z, or negative 2 times 1. So now that we've answered the question, let's go ahead and interpret the results. So here's the given vector field. Here it is again with less vectors in the vector field. And the curl vector field is this vector field here. Remember, the vectors in this field point in the direction of the axis of rotation, and the magnitude of these vectors represent how strong or how fast an object would rotate at that location. So if we take a look at the curl vector at the point 6, negative 3, 1, this is the vector here. So at the point 6, 3, negative 1 in that field, the axis of rotation would be along this vector, and its magnitude would tell us how strongly it would rotate. And then lastly, the direction of rotation would be in the direction of, if you take your right hand and point it in the direction this vector points, and then close your right hand, the rotation would be in the same direction as your fingers move as you close that right hand. And that'll do it for this video. Thank you for watching.